Alright, so just remember those rules. We have those rules for capacitors in series and caps in parallel. You should have these already, but let me just remind you. In series, the equivalent capacitance is 1 over C1 plus 1 over C2 plus ... And so we'll do some equivalent problems to give you some extra practice. And then for those in parallel, the equivalent capacitance is just the sum of all the capacitors. And you probably done, have you done the resistor lab yet? Yeah. So you saw that with resistors it switched. With resistors in series, you just add up the resistances. For resistors in parallel, you do the whole inverse thing. So that's one thing that's different with resistors. But a lot of the other stuff is the same. Capacitors in series have the same charge. Capacitors in parallel have the same voltage. For capacitors in series, Q is equal to CV for any one of the individual capacitors, and the same is also true for capacitors in parallel. Q is equal to CV. And then further, for capacitors in series, V total is equal to V1 plus V2 plus V3 plus however many capacitors there are. And then just a little extra explanation here. Capacitors in series have the same charge. They also have the same charge as the equivalent capacitance. And capacitors in parallel have the same voltage. They also have the same voltage as the equivalent capacitance. I'll show you what that means. We'll do an example. Okay? So let's start first with a series capacitor, 3 capacitors in series. So imagine I have a battery. I have 1 capacitor, 2 capacitors, 3 capacitors. Let's do 3, 6, and 12 microfarads, and we'll say this is 12 volts. Does that work? 3, 6, and 12. If it was 9. Yeah, I think that'll work. 3, 6, and 12 microfarads, 12 volts. I want to know a couple things. I want to know what is the equivalent capacitance, and I also want to know what is the voltage on each, and what is the charge on each. Alright, so can you find the equivalent capacitance of that? How would you find the equivalent? Or you can work it on your paper. I'm going to give you a little head start and then I'll show you. Right. 1 over 6, 1 over 12. That's going to be 4 over 12 plus 2 over 12 plus 1 over 12. Well, that doesn't work out either, but that's okay. We'll just do the decimal. So just tell me what the decimal is. I'm going to write it up here. What is it? 0.7 microfarads. Let me double check that. Seem uncertain. 3 inverse, 6 inverse. Yeah, 1.7, 1.4. Listen, on the test, the numbers will come out evenly. I'll pick numbers. It's just sort of hard for me to do it on the fly. All right, so that's the equivalent capacitance. Now I want to know the voltage on each and the charge on each. So remember our rules. Capacitors in series have the same charge. They also have the same charge as the equivalent capacitance. So how would I find the charge on each of these capacitors? Now, I know that the charge is going to be the same for all 3. They have to be because they're in series. So find the charge. How would I find that charge? Close. So you do want to start with this, that Q is equal to CV. That's also one of our relationships we need to know. right? So I'm just going to take that equivalent capacitance, this capacitance, and multiply it times the voltage. And that's going to be about 20 or so. Yeah, 21 microcoulombs, what I get, 20.6. So that's the charge on each capacitor. I have 3 microfarads here, 6 microfarads here. I have 21 microcoulombs on all 3 of those. So we've gotten this one, we've gotten this one, and now we need to find the voltage. Now, with capacitors, if you know either of the two, we have this relationship Q is equal to CV. So if you know 2 of those, the third one is, you can find the third one. So once you get to this point, finding that the voltages on each is sort of trivial. So I just say V is Q over C. And I do that for each of those. So for example, on the 3 microfarad, it's going to be 21 microcoulombs divided by 3 microfarads are 7 volts. On the 6 microfarad, it's going to be 21 divided by 6. That's going to be 3.5. And then on the other one, it's going to be 21 divided by 12. Oh, what's that? 1.75? Yeah, 1.75. All right. Want to make sure you recognize here that all 3 of these have to add up to equal what? That's right. So they all have to add up equal to 12. I rounded off here, so that's 10.5, 11.5. It's a little bit more than 12, but that's because I rounded along the way. On the test, you'll have very even numbers. Okay. Capacitors in parallel, those are a little easier. For capacitors in parallel, really all you have to recognize is that each capacitor acts independently. So if I have 2 microfarads, 3 microfarads, 10 volts, if I want to know the charge on each capacitor, I just need to recognize that each of these have 10 volts on them. Right, and then it becomes pretty simple. So this is probably the simplest circuit that you could have. You could see it on the test, but probably not. Probably if you had either a series or parallel, probably you're going to see a series circuit. Those are a little more complicated. Okay? This too fast? Is that right? Okay. Okay, so now the hard one, and this is what you'll have on the test, are combination circuits. You'll have several like this. So let's say let me think about something right quick. I think it's 3. No. So let's say that I have a 3 microfarad, a 2 microfarad over here, a 4 microfarad, 4 microfarad, and a 2 microfarad. Make sure that works out. No, let's make this 4 microfarad, I'm sorry. Yep, that'll work. And then I have 12 volts. Okay? So, a couple things I want to know. Actually, let's just say I want to know the voltage and the charge on every capacitor. Now, in practice on the test, I'll give you I'll give you just, one or two of the capacitors. I want to know the voltage or the charge on one of those, but you should be able to find the voltage and or the charge on every capacitor. The first step that you want to do is to find the equivalent capacitance. So where are you going to start on this capacitor to find the equivalent capacitance?
The upper part of the chart.
That's right. Yeah, you start with those two 4 microfarad capacitors. So go ahead and find that equivalent capacitance. You start with that one, as you know, because that is the simplest portion that is only in series or only in parallel. You'll get used to this. I'll use some pretty common numbers. So 4 and 4 are ones that I like to use because they work out simply. What'd you get? That's right. So 1 over a half is equal to 2. Now, let's go ahead and skip a step, and we'll redraw the circuit here in just a second. But let's now say, what is the equivalent of this? So now I have a 2 and a 4 in series, or in parallel rather. What is the equivalent of that? It's just going to be 2 plus 4 is 6. So I say 2 plus 4 equals 6. And now I'm going to redraw this circuit. It does really help, especially when you're first starting, to redraw the circuits. It helps you to see sort of how the capacitors are all laid out. I have a 3 microfarad, a 6 microfarad, and a 2 microfarad. You have 2 microfarad, and I have 12 volts. Why don't you go ahead and find the equivalent capacitance of that 3, 6, and 2, which are also common numbers that I like to use because they work out easily. What'd you get there? You got it. It just equals to 1, right? You think about your common denominator, which is going to be 6. This denominator here becomes 2 6 plus 1 6 plus 3 6. That's just equal to 1. Like I said, be on the lookout for those easy numbers. I'll try to give them to you the best you can. All right, so this whole circuit is just equivalent to 1 microfarad, 12 volts. So now I can begin to step backwards, because I know that this 1 microfarad capacitor will have a charge, remember Q equals CV, it will have a charge of C, which is 1 microfarad, times 12 volts. It will have 12 microcoulombs of charge. What will these capacitors have for charge? Remember your rule about capacitors in series? Capacitors in series have the same charge. They also have the same charge as their equivalent capacitance. So whatever the equivalent capacitance is, the capacitors in series will have that same charge. That's right. So I'm going to have 12 microcoulombs here, 12 microcoulombs here, and 12 microcoulombs here. Now I can also find the voltages on each of those. How would I find the voltages on each of those? Yeah, you're right. Yeah. Coulombs by the what? The F? Yeah, the farads. So right, V is Q divided by C. It's not really imperative that you know the language or the words and stuff, but it'll help you think it through if you know the words in your mind. So practice that. So what are the voltages here? I'm going to write out the voltages. What's the voltage for the 3 microfarad? Right, that's 4 volts. And the 6 microfarad? 2 volts. and 6 volts. And notice that 4 plus 2 plus 6 equals 12, as it should. Now you can maybe just look at this. No, you probably couldn't just look at it. Maybe. You could maybe look at that and say, yeah, that has to be distributed as a 2, 4, and 6, but probably not. You probably just want to work through this. Okay? This process, though, will work for any numbers. All right, so we already know the answers for some of them. Like we know the answer for this one because this capacitor is the same as this capacitor, and this capacitor is the same as this capacitor. So now we need to figure out this thing in the middle here. But you might just be able to look at it, and you might be able to say, well, I know the voltage on all 3 of these capacitors. You know the voltage here? On the bottom 4 microfarad capacitor? Just guess if you want. What do you think?
Would it still, would voltage, would it still be 12, right?
No, it's not going to be 12. I understand why you're saying that, but that's not the right answer. But you're thinking on the right direction. The rule for capacitors in parallel is that capacitors in parallel have the same voltage, and they have the same voltage as the equivalent capacitor. So what is the voltage across the equivalent capacitor of that whole 4, 4, and 4 bit? What's the voltage across the equivalent for those 3 capacitors? No, it wasn't 1. That was the total equivalent capacitance was 1. But we took this branch right here, and we said, I know the equivalent capacitance of this branch alone. What was it?
Was it 2?
Up here was 2, right? This part was 2. But this whole thing, what was the equivalent capacitance? It was 6. That's right. So here we have 2 right here, and then we added it to our 4, and that gives us 6 microfarads. All right. It's good to make mistakes right here. This is where you need to make mistakes. So the equivalent capacitance of this whole thing right here is 6 microfarads. It is this capacitor right here. So that 6 microfarad capacitor has 2 volts across it. What is the voltage then across these 4 microfarad capacitors? No. I have 2 volts across here, across this capacitor, which is the equivalent. Capacitors in parallel have the same voltage as their equivalent capacitor. So I'm going to have 2 volts here and 2 volts here. Because capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitor. You with me? Sort of. Okay, we'll do another example. So, voltage here is what? Is going to be 2 volts. Up here, I have 2 volts across these capacitors, these 2 identical capacitors. So what is going to be the voltage across each of the capacitors? These are capacitors in series. And if you remember your rule for capacitor in series, let me go back to that. The rule for capacitors in series is that the total voltage across those capacitors in series have to equal the sum of the voltages. So I have 2 volts across these 2 capacitors. What's the voltage across this capacitor? It's going to be 1 volt. And here? Only because they're identical. If they were not identical, they would have dissimilar, they would have different voltages. All right? So we'll do one with different. So this would be 1 volt, and this would also be 1 volt. That's a good example of a test question. Let me show you another way, because often students see a circuit on the test, and they just don't know how to get it into this form. So a lot of students can work problems that look like this, but when they see the problem on a test, it doesn't look exactly like that, and they just sort of freak out. So let me show you this circuit, the identical circuit, more like what you might see like it on the test. All right, these two circuits are identical. And in fact, this is the way that I'm going to draw it on the test. But you need to understand that these are identical. Often what students get confused is that they think that these are somehow parallel, the 3 and the 2 microfarad, but they're really not at all. And the way that you test that is you start at the big side of the battery, you go along through the first capacitor, and you come to your first junction. And at your first junction is where you draw this thing. All right? At your first junction shows you where your first parallel branch begins. So I have this parallel branch right here that starts at the first junction, goes through, and comes back and ends at the next junction. Okay? And then this is in series. So this circuit is identical to this circuit. And in fact, you're going to see a circuit that will look more like this. I'll show you an example on an old test. Excuse me. Want to pull up an old test? Is that okay? Let's see, probably most of these are going to be exam 2. Let's do S15. Is this one we have in our book? I forget if we have spring 15 or not. Do you know? Can you look in the back and see if this is the same as what we have in the book? It's exam 2, number 5. Oh, no, that's 2013. Okay, we're good. Yeah, that's 2013. Okay, so let's do this. You see a lot of similar circuits, but they're all a little bit different too. All right, so we want to find the equivalent capacitance of this circuit. Where are we going to start? At the top, because those are in series. They're only in series. What is the equivalent of a 3 and 6 in series? This is really something that you should just try to memorize, because you'll certainly see 3 and 6 in series for capacitors. But go ahead and work it out. It's actually going to be, yeah, 1 over 2 6 plus 1 6. But 2 6 plus 1 6 is what? 3 6, which is really a half. Right, so it's 1 over a half, which is half goes into 1 twice. So the equivalent of these is 2 microfarads. All right, what are we going to do next? That 2 microfarad, what do I do next? Well, no, I want to find the equivalent capacitance first. I just found the equivalent of the top section. All right, and now I have, I want to combine, I want to find the equivalent of the next bigger section. What is that going to be? Right. So I'll find the equivalent of these two. These are in series, a 2 are in parallel, a 2 and a 2 in parallel. So what's the equivalent of that? That's right, 2 plus 2 is equal to 4 when they're in parallel. And then I have my battery, a 4 microfarad, another 4 microfarad, 12-volt battery. I need to find the equivalent of this. Again, another combination that you should probably just try to memorize or at least be familiar with, that if you write it out like this, you'll know the answer pretty quickly. Or you can use your calculator, that's fine too. What is this? Quarter plus a quarter is a half, and 1 over a half is 2. Right, so my equivalent capacitance is going to be 2 microfarads. Now, the next question asks, what is the voltage across the 3 microfarad capacitor. Now, I want to remind you that we have the equivalent circuit looks like this: 4 microfarad, 4 microfarad. That was our next to last step. And now I want to know the voltage across this capacitor. What is the voltage across that capacitor? And in the course of that, you can probably tell me the voltages across all the capacitors. What is the voltage across this capacitor? No, it's not 3. That's a good guess, though, but these capacitors are in series. You were thinking that they were in parallel, and that would have been correct if they were in parallel, right? Because it would be Q over C. No, what did you say, 3? No, yeah, that's not right. Never mind, I'm sorry.
So it would be 6.
It is 6, right. So I have 6 volts here.
Series they add up to 12.
That's right. These are in series. Because they're identical, only because they're identical, do you get 6 volts and 6 volts. All right? We'll see what happens when they're not identical, when we get it to that 3 and 6. So that means, this capacitor is this capacitor. So what is my voltage across this capacitor? Thinking about what's going on here, because that's the equivalent of that 3, 6, and 2 all together.
So those times 3.
Mm-hmm. In fact, we can think of these top 3 as looking like this: a 2 microfarad, because that's the 3 and the 6 together, and a 2 microfarad. And they each have 6, or sorry, never mind. What is the voltage across this capacitor? No? Let's think back to our rules. Capacitors in parallel have the same voltage. Yeah. It's going to be 6, right? So I'm going to have 6 volts on this capacitor, which is the same as the one over here. I also have 6 volts on this capacitor. Okay, so now it gets a little tricky. I really want to know the voltage across the 3 microfarad capacitor. There are a couple different ways you could do this. Let's do it the hard way first. Capacitors in series have the same what? That's right. Capacitors in series have the same charge. What is the charge on these capacitors? Capacitors in series have the same charge. They also have the same charge as their equivalent capacitor. Right, that's the question you want to ask yourself. What is the charge across the equivalent capacitor? Anytime you know 2 quantities on a capacitor, you can find the third. Remembering our relationship, Q is equal to C times V. And there I know C, which is 2 microfarads, and I know V, which is 6 volts. So what is the charge on that equivalent capacitor? That's right. I have 12 microcoulombs on this capacitor. So what does that tell us about these 2 capacitors? What is the charge on the 3? What is the charge on the 6?
Since they're in series, they're both 12.
That's right. So I'm going to have 12 microcoulombs on both of those. I have 12 microcoulombs here and 12 microcoulombs here. And now, boom, I have 2 quantities. I have C and I have Q. So I can find V. What is V? The potential or the voltage on that 3 microfarad capacitor. There's going to be 4 volts. That's exactly right. So I have Q over C, 12 over 3 are 4 volts. Now, what is the voltage across this capacitor? If this is 4 volts and this is 6 volts, the equivalent, what must be the voltage across the 6 microfarad capacitor? It has to be 2. And you can see that, right, because I have 12 microcoulombs, 6 microfarads, 12 divided by 6 has to equal 2. But also notice that 4 plus 2 here and here is equal to 6. So we could have just bypassed all this business with a charge, and we could have said, well, I have these 2 capacitors. One of them's bigger and one of them's smaller. One of them's bigger by a factor of 2. And when I have a bigger capacitor, the voltage is going to be smaller. When I have capacitors that have constant charge, as these do, if C goes up, V goes down. And so you see, these capacitors, which are off by a factor of 2, their voltages are also off by a factor of 2. One's twice as big as the other. And so I could have said, well, the voltages are going to be distributed across these 2 capacitors. It has to be 4 and 2, because I know that the 3 microfarad capacitor has to have twice the voltage as the 6 microfarad capacitor. And I also know that the sum of them have to equal 6. So that's a nice little trick that you'll probably be able to use several times on the coming exam that saves you a lot of time and a lot of headache in figuring out the charge. It's a little tedious to go through this whole process with capacitors in series, figuring out the charge. But if you can get to that point where you can see how the voltages are distributed, it'll really help you. And that's going to be a common capacitances that I'll use, 3 and a 6, or 2 and a 4, or 1 and a 2, stuff like that, where they're off by a factor of 2. So remember that the smaller capacitor carries a bigger voltage, and the bigger capacitor carries a smaller voltage by the same factor as their capacitances are different. That will help you with the resistors too, because if you can begin to do that with capacitors, you'll also be able to do it with resistors. And since this test will have both capacitors and resistors, that's going to be a pretty big chunk of the test. I mean, you're talking probably 6 or 7 problems that are circuits, which is, a quarter or a third of the test.
So resistors usually be capacitors. Yeah. Series and the parallel, one of those will be switched for resistors.
Yeah, but a lot of those other rules will still hold the same. So you'll see, we're going to get into resistors in series and parallel next week, and you'll see how they're different, but also more importantly how they're similar. It's really just the equivalent stuff, and with resistors we don't talk about them having charge. They don't really hold a charge. Instead, we talk about the charge flowing through the resistor, which is the current. But you're going to see that it's very similar. Similar, but a little bit different. So you just have to be careful with it. All right, can I clear this? We'll do another one? Okay, so let's see if there's another good one here. Now let's try this one. This one is, let's do this circuit, but I want to know, this one asks for the energy. We'll do that. But yeah, let's do the energy first on this 2 microfarad capacitor. And then I also want to know the voltages on all the capacitors. What is the voltage on that topmost 2 microfarad capacitor? Well, no, on the one that's circled here. What is the voltage on that capacitor? No, it's not going to be 6. Try again, because I think when you hit on the answer, you'll see. Let me redraw this circuit a little bit, okay? Because I can take the equivalent of the 3 and the 6. I don't have to do that, but I can. So I have a 2, a 2, and a 2 microfarad capacitor. All I did was I just took the equivalent of these two. That might help you a little bit. What is the voltage across this capacitor.
Voltage.
That's right. I'm going to have 12 volts here, 12 volts here, and 12 volts here. And then here, if I want to find the energy, it's just 1/2 CV squared. You just need to know how to use that formula. It's on your equation sheet. 1/2 of 2 times 12 squared. That's 144 microjoules. All right. But let's go ahead and take a look and see what are the voltages across all of the capacitors. Now, we've already said that this voltage is 12, this voltage is 12, and the voltage across this equivalent capacitor is 12. But what is the voltage across the 3 microfarad capacitor? Well, let's try that trick where you, or it's not a trick really, but think about how the voltages should be distributed across the 3 and the 6 microfarad capacitor when they're in series, just like we did last time. That's right. The 3 should have the higher voltage by how much? By what factor? Right. And they should add up equal what? That's right. So what is the 3 microfarad? That's right. That's right. Okay? Easy, right? Yeah, so once you start to get it, it will be easier and easier. Notice you could have done it the hard way. Right? You could have said, well, gosh, this has 24 microcoulombs. So this one has 24 microcoulombs, this one has 24 microcoulombs, and then I could find the voltages by saying Q over C. So that would be 24 divided by 3 is equal to 8, 24 divided by 4 is equal to 6. So you could do it that way too, where you find the charges, but I think it's a lot easier just to look at the capacitors. Now what if instead of 3 and 6, what if instead we had 6 and 6? What would be the voltages across those two capacitors? That's right. I would have 6 volts and 6 volts. Because they have this 12 volts across them here, they're going to split it because they're identical. Let me see. What if... what if, instead of being 3 and 6, it is 3, I think it's the word, hold on, let me think, 3 and 1 microfarad. Which one's going to have 9 volts?
3 would have 3 and 1 would have 9.
You sure? Oh yeah, no, you are right. Yes, you are sure. Okay, I wasn't sure. Yeah, so this is 3 volts and this is 9 volts. Now you see in this one, it's really nice to be able to do it this way because if I think about the equivalent is 1 over 3 plus 1 over 1. That's 1/3 plus 3/3, so that's 4/3. So it's like 3/4, and you start getting into fractions and all this, and it just gets a little more complicated. So that's the equivalent capacitance, and then you have to find the charge. And anyway, the math just gets more complicated. But if you can just look at it like you just did and say, well, gosh, that one has to have a third. The 3 microfarad has to have 3 volts, and the 1 microfarad has to have 9 volts. Your life will be a lot easier. Okay? So let's look at some of them. You feeling a little better about these? You seem to be getting it better. All right, let's you'll find that if you master these now, you'll find that resistors are a lot easier. Oh, let's try this one. What is the voltage across the 6 microfarad? If you need to work this out, that's fine. Might be able to reason it out, but it might be easier to just figure out what is the equivalent capacitance. Figure out then the charge, and then figure out the voltage on each. Is that right? 1 over 1/3 plus a 6 plus a 1/2 That's 4/12 plus 2/12 is 6/12 plus 6/12. No, I think it's 1, isn't it? Am I doing that wrong? I could be doing it wrong. Yeah, so it's just equal to 1. Yeah, if you're not certain, I mean, it's okay to write it out. It's even okay to use your calculator, especially if you're doing 3 like that. But that is a common combination that I'll use, so you'll probably see it again, or you could see it again. All right, so what is the voltage then, or what is the charge on the 6 microfarad capacitor? Right, I'm going to have 18 microcoulombs, Q equal to CV. I'm actually going to have that on all 3. Because they're in series. Capacitors in series have the same charge. So what is the voltage on the 6 microfarad? Right, 3 volts. I can find these others, 6 volts. You know, this 3 volt is half the capacitance, so it has twice the voltage. And then over here, of the 6 microfarad, this 2 microfarad is a third the capacitance of the 6 microfarad, so it's going to have 3 times the voltage, or 9 volts. So I have 6, 3, and 9 volts. This is looking for the 6 microfarad, so it is B here. All right, let's pull up another test. So which one is that? 15. Okay to just do more circuits? Okay, let's do this number 1 then. So similar but different. I want to know the equivalent capacitance first, and then the voltage across C3. The equivalent capacitance first. You got it? Mm-hmm. Right. That top section, the C3 and C2, they simplify down to just a 2 microfarad. So then you have a 2 microfarad and a 2 microfarad. What's that going to be equal to? No. In series, what do you do for capacitors? If you forget on your test, it is on the equation sheet, but it's good to just have it at the front of your mind. It's going to be 1, right? 1 over a half plus a half is equal to 1. So the equivalent capacitance is 1 microfarad. What is the voltage across C3? Now remember, you already told me that our equivalent circuit, or one of our equivalent circuits, looks like this. C1 is 2 microfarads, and then I replace those top 2 capacitors with another 2 microfarad capacitor, and I have 12 volts. And now I want to know what is the voltage across this capacitor. What do you think that would be? Should be able to tell me just by looking at it without using your calculator. That's right. All right. Just make sure you reason it correctly. I have 2 microfarad capacitors, so each of these are going to have 6 volts. That's what you were thinking? Both of these, which are in parallel, then, will also have 6 volts. All right? So see, that circuit you should have just been able to look at and answer both questions, hopefully just with a little bit of math in your head. But if you can't do it in your head, that's okay. You can just do it on the paper, but be more deliberate about it. Okay. If we want to know the charge on C1, We already said that this is 6 volts, so if we want to know the charge, I just say Q is equal to CV. It's going to be 12 microcoulombs. Similarly, 6 microcoulombs here and 6 microcoulombs here, because they all had 6 volts. Isn't that right? Yeah, they all had 6 volts. So I just multiply C times V to get the charge. Anytime you know two quantities, you can find the third one simply. Okay. Equivalent of these three capacitors? Three 3 microfarad capacitors in series? That's right, yeah. You know how to do it. Be confident in what you're doing. So it's 1/3 plus a third plus a third. That's equal to 1. What if I have those same capacitors, but not in series, but in parallel like this one? What's the equivalent of that?
No, wait, sorry, that'd be 9.
Yeah, it'd be 9, yeah. Don't apologize. All right, yeah, so the answer there would be 9, because I just add them up. 3 plus 3 plus 3. All right? Let's look at number 7. Two identical capacitors are connected in series, and two, each identical to the first, are connected in parallel. The equivalent capacitance of the series connection is what? Is it twice, 4 times, half, 1/4, or is it the same as the equivalent capacitance of the parallel connection? So the first is 2 in series, C and C. The second is 2 in parallel, C and C, like this. I want to know, what is the relation of 1 to 2? Is 1 twice, 4 times, half, 1/4, or is it the same as the other? You might want to sketch it out and sort of think about what is this? This is spring 14. Yeah, this is a good test. No. Is it going to be bigger or smaller, the series, than the parallel? It will be smaller, right? I know the over here, the capacitance is 2C, C plus C.
Yeah, I was thinking when I sketched it out, for the series I had, for example, 1 for the series. For parallel, I had the same thing. So I was thinking in my head that the series, the parallel would be twice the series. It'd be half that.
Well, let's see. So here I have 1 over C plus 1 over C. If you want to put in numbers for C, that's fine. But this is going to be 1 over 2 over C, which is C over 2. All right, so number 1 is what times number 2? It's not half. It's a fourth, right? C over 2 is equal to 1/4 of 2C. Alrighty? Alright. That'll come with practice. Let's just do one more and we're going to wrap up. That's okay. Ooh. Okay, this one was complicated, but it's not. You don't want to know the charge on C2. What do I do with this circuit? No, it's simpler than that. It's actually really simple. It's just plain parallel. Often in circuit diagrams, you'll see these. It's really just drawn to save space, where they'll cut across diagonals instead of drawing them out on a grid like we usually do. And so you could see it on the test. It's a common thing in circuit diagrams to cut across a diagonal. But you can think about it. I have this junction right here. I can move it anywhere along this line as long as I don't cross a device or I don't cross another junction. So I can move it anywhere along this line, and I can move this part anywhere along this line. So I could redraw this just as 3 parallel capacitors like that. And then it becomes pretty simple, because what is the voltage on C2?
With all those sections parallel, so it'd be 12.
Right, it's going to be 12 volts. That's right. You're a pro at this now. All right. Let me stop there. Is that okay? All right.